Thank you very much for introduction, and thanks for organizing, for giving us possibility to speak here. So it's a joint work in progress with Ray. I hope it will be finished in archive soon. It was a long project. So I'll speak about Schubert calculus for quantum Grassmannians. So classically, Schubert calculus, in particular, talk about ring structure on cohomologies of homogeneous spaces. Well, precisely Grassmannians. There is a deep connections with the representation theory. So we know that classically, as a cohomology ring of Grassmannians is isomorphic to the quotient of the Grothendieck ring of representation of GLM. So in this talk, in this work, we are trying to get the same result for the quantum case, and this is a report on the progress. So I will start, maybe you've seen the definition of UQ of G so many times during this conference, but let's fix the notation. So we start with some simple finite dimensional complex Lie algebra, which is defined by Cartan matrix. With say Qi defined in the following way, and then Drinfeld-Jimbo quantum group is defined as an associative algebra generated by symbols EI, FI, KI, KI inverse, modulo these relations. So we already know that since that this guy tells you that E weights of EI and FI, and this is a kind of a commutator, and we have a deformation of a quantum C relations. And maybe I just comment to what was said before, that if you look at this object as an algebra without co-structures, that it's not so far from the classical universal enveloping algebra. So, for example, if you instead of Q consider that formal parameter H, then it will be just isomorphic. But because of the Whitehead lemma and vanishing of the second cohomologies of modules of simple Lie algebras, but what really makes it unique, it's something new. It's Howe algebra structure, which is deformed. So product becomes non-symmetrical one. You can see here and here. And in this talk, we will speak about compact situation. So we choose only one compact real form. So the star structure is defined like that. And as we heard many times, that there is a nice subcategory of representation of Drinfeld-Jimbo quantum groups, which is as category equivalent to representation of the corresponding Lie algebra. So as usual, we can speak about weight lattice, take some dominant integral weight. There is a module which is a quotient of a Rham module with the highest weight with the following properties. And yeah, such representation we'll call type 1, finite dimensional type 1 game. And we can use a weight theory here. The weight will still be functional on element dual to Cartan subalgebra of classical Lie algebra. Just it will be multiplied not by this scalar product, but Q to the power of it. So starting from that, we can construct quantized coordinate algebra for the corresponding compact simply connected group. How we can do that? First, consider the functionals defined in the following manner. Then the coordinate space of some representation is just a linear span of such functions. Then, if we will take now direct sum of all coordinate spaces for all finite dimensional type final representations, then this space could be endowed with algebra structure, co-algebra structure. So it's and more Howe algebra. And classically, it will give us exactly these coordinate functions on the corresponding Lie group G. I'm stressing that we are speaking about compact situations. So G here is a compact, simply connected, complex algebraic group such that its Lie algebra is G. So now we have a terminology of quantum groups. We can speak about the homogeneous spaces. One of the ways to look at constructing homogeneous spaces is flag manifolds. Basically, you should construct a subgroup of your Lie group by looking at the Dynkin diagram and crossing some nodes. But it's now we should reformulate what is a subgroup. So it could be done in the framework of quantum homogeneous spaces. Let pi be a surjective Hopf algebra map between two Hopf algebras. You can think about A as a big group. Sorry, A should be coordinate algebra on a big group and H coordinate algebra on a small group. So because small groups lives inside the big one, we have a map go in opposite direction for functions. Then we can endow A with H, right H coaction in a simple manner, and consider the corresponding co-invariant space, and B, and we will call it quantum homogeneous space corresponding to map pi and pair of Hopf algebras A and H. And again, you can think about B as an algebra of function, coordinate function on the corresponding homogeneous spaces. So now there is a recipe how to obtain very nice families, as I said, quantum flag manifolds. So just take your Dynkin diagram, put some crosses on them, and let S will be the set of non-crossed vertices. Then we can consider the corresponding quantum Levy subalgebra. So it's generated by all Ks. So our quantized Cartan subalgebra stays the same, but we choose only non-crossed E's and F's. Then with a bit of magic using this inclusion, we can define the corresponding projection into dual of this quantum Levy subalgebra, which give us a structure of a quantum homogeneous space. So pretty much we define our quantum Levy subalgebra using this projection, and the corresponding quantum homogeneous space is called quantum flag manifolds. I would stress that we also have duality between co-modules of quantum group, quantum coordinate algebra, and modules over the Rham-Jimbo quantum group. So instead of Howe invariance here, I could write just invariance with respect to this action. All right. So now we want to, when we have some homogeneous spaces, we want to speak about homogeneous vector bundles. And usually, classically, it's done by inducing this representation from the small group to the big one. And the same works here, a bit more fancy manner using this Takeuchi categorical equivalence. So as a model of our homogeneous vector bundles, we will look at H co-modules. So co-modules over our quantum Levy subgroup, or it's a modules over quantum Levy subalgebra. Then this category will serve for sections of a homogeneous bundle over our quantum homogeneous space. So remember that we can multiply sections from the right and left. So that's written here, but in this category sub-zero, we're considering trivial the actions on the right. And remember that on section of homogeneous vector bundle, you can act by a big group G. So that's reflected in the existence of this co-module structure with respect to A. And there is pair of functors that defines equivalence of these two categories. And you can say that starting from some cohomodule, we can construct a corresponding quantum homogeneous vector bundle, and vice versa. From quantum homogeneous vector bundle, we can see how it looks locally, because usually the guys in the global category are finite dimensional, and the guys in the small category is just vector spaces, so it's comodules. So when I will speak about something having the dimension, I will always speak about dimension in the local category in this game. And yeah, another good thing is that it's a very nice equivalence. It's also monoidal equivalence, but it's some details under the carpet. Going back to Henrik's curves, we consider differential calculus to get some cohomologies. I will end up definition with a couple of extra structures. First, we need a star structure because we're speaking about complex things. So star calculus is a calculus with involutive linear map star, such that it satisfies the following conditions. And obviously, if you have a star calculus, and you will have your base algebra, your B should be also star algebra. Now, we want to speak about invariant forms. So our differential forms should form a homogeneous vector bundle. So covariant differential calculus is a differential calculus endowed with a structure of a cohomodule such that the following condition holds. So we have a nice commutation relations between differential and a coaction. Again, you can write a couple of diagrams, reversal errors, and you will get the classical situations that the Rham differential is equivariant on the corresponding homogeneous space. And as I mentioned, when we will speak about dimensions of a calculi, we'll speak about dimension of the corresponding cohomodule, H cohomodule in the local category. So it's like you're looking. Classically, it will more or less correspond looking at the fiber at the point. So the main hero of this talk will be quantum Grassmanianns, which is a member of huge family of irreducible quantum flat manifolds. What makes them irreducible? For example, you can take as a definition that if you look at it as a corresponding isotropy representation, it will be a sum of two guys. It will be some irreducible LS module over Levi subalgebra, and it's dual. Or you can just postulate that they form this list. So many of the things that I will tell today applicable for the whole list of the reducible quantum flat manifolds. But the final theorem will be formulated for quantum Grassmannians, which corresponds to the first line. So you take a Dynkin diagram of AN and put a cross somewhere. So why is that special in the quantum world? First, for them, almost 20 years ago, we have a nice calculus which satisfies many nice properties. It was found by Heckenberger and Howe. So first of all, it has a classical dimension. And there's a big problem in the theory of calculus over quantum groups, because we know that if you consider some bicovariant calculus on quantum group itself, they have a problem with dimensions. The dimension is usually bigger. It's also star calculus, and it covariant, so it lives in the right category that we defined before. So it forms a homogeneous vector bundle or over the corresponding quantum flat manifold. And so let's play to compute some cohomologies of this differential gradient algebra. We need some tools. Classically, it is one way to compute this cohomology is to use complex geometry. So let's start with the complex structures. It's just definition reformulated from some theorems from the classical complex geometry. So our calculus should be bigraded, satisfying the following three conditions. And we can project now, split our differential in two parts, holonomic and anti-holonomic part. bar and del bar. And if you have a complex structure, then indeed our Rham splits into two parts. So it's a sum of holomorphic, anti-holomorphic differentials, and they anti-commutes, and they are also differentials. So it's a bicomplex. If it was a star calculus, we also require the following conditions. Nice. So a complex structure called covariant if the corresponding Z grading is a grading in category of A comodules. So as you would expect it classically. So it should be object in this category. And well, from that we get automatically that it's that every piece of the grading is a sub B bimodule. And differentials behave nicely with respect to comodule structure. Probably Ray should help me. Who proved it that we have a complex structures for Higginberg and Cope? So it's like, yeah. So it's basically folklore. Yeah. So one nice thing about the Higginberg and Cope calculus that it's also admits this complex structure is factorizable. It's very nice, and there is precisely two complex structures on this calculus. It's a complex structure and its opposite. So opposite complex structure could be just obtained by flipping your N2 grading. So let's go further. First of all, this is example. Consider just quantum CP2. We have its quantized Rham complex given by Higginberg and Cope calculus, and its corresponding B complex given by the complex structure. Looks very nice. What we can get further? Well, we can try to speak about Hermitian structures as defined in Ray's paper from 27. So what is a quantum Hermitian and Keller structure? So Hermitian structure on some calculi is first complex structure. Second, we need some real form that belong, which means that it belongs to the following component, homogeneous component of grading, and also behave nicely with respect to star, and a bunch of isomorphisms given by the following formula. Classically, you can derive it, but up to now, in quantum setting, it's a part of the definition. So it's a Hermitian structure and a Keller structure. It's when you have a Hermitian structure such that the corresponding form is closed, then you call this form Keller form. And as it was shown by Ray for complex projective spaces, Higginberg and Cope calculus admits a covariant Keller structure, and then later, in some computational way, it was extended by Marco Matassa for all family of irreducible quantum Flagg manifolds. Perfect. Let's go further. So usually, when we have some Keller structure, we can speak about Hodge decomposition, and it's one of the main tools how you compute these cohomologies. Let's try to do the same. So first, we start with the Lifshitz decomposition, which is a part of a definition of Hermitian form. So as classically, we defined space of primitive forms as a kernel of Lifshitz operators. Then we can define a Hodge map by just postulating Weil formula for it, and define a Hermitian metric using this form. So as usual, you take a star, go up, wedge, go down. And as it was shown by Ray, Jan Stolicek, and Adam, this metric behaves nicely with a star structure. So we can take adjoints with respect to this metric. So if we will take adjoints with respect to Lifshitz operator, we'll get another operator lambda in the following manner. And it will give us some SL2 triple, as it is explained to us, yes, in the previous talk by Spiros. It's an example of this dual pair between symplexic group and SL2. So it's quantized perfectly in this iteration. And now we have an even nicer decomposition with respect to primitive forms. And these two operators, Lefschetz operators and the dual to them. So let's go further. We can also take the adjoints of our differentials and consider the corresponding Laplacians. So this lemma states that we can take the corresponding adjoints. Let's consider on the Laplacians and existence and the corresponding harmonic forms with each of these differentials, and existence of the Kähler structure, as Ray taught us, guarantees this decomposition of calculi into harmonics and image of differentials. So basically, to compute the cohomology, you should compute harmonic forms. Yes, so this is graded isomorphisms. So you can think about cohomologies with respect to whole Rham or holomorphic and anti-holomorphic particles. Now we can define an arc of a character map in the quantum setting in the following manner. So using this projection, and we can show that it's an injective algebra map. So it basically tells us that if you'll consider the just invariant harmonic forms, we can still recover some information about our cohomologies, and we have a conjecture that this map is an isomorphism. And one of the ways how to prove this conjecture classically is to use Dirac operators. But as you've seen by Pavlov's talk, we still have very few examples of Dirac operators for quantum groups. So it's some work in progress by Pavle and Petr Sonberg and me and Pavle, as it presented at the beginning of the afternoon session. So now we have all tools to describe cohomologies of quantum Grassmannians or any reducible quantum flat manifolds, assuming this conjecture that all harmonic forms will be invariant. So now I will go down to earth, and instead of speaking about some general quantum reducible quantum flat manifold, I will speak precisely about quantum Grassmannians because it's the most interesting classical case. So in this setup, our G is GLM. This is Levy subalgebra. We have, let's define the following notation. So our V will be space of holonomic forms. V star, its dual, will be space of anti-holonomic forms, and the corresponding local versions of a calculi will be this quantum exterior algebra. And it was later discovered that they could be characterized as this quantum Bernstein-Zvitsnagel exterior algebra that was mentioned by Pavle in his talk. And as a module over quantum Levy subalgebra, we know that the local version of our holomorphic part is just this box tensor product of dual modules. So box here means that this is irreducible module over UQ of GLM with this highest weight. And this guy is a dual of irreducible highest, irreducible UQ SLN minus M module with this highest weight. And the same for the space of anti-holomorphic forms. Now, using the analog of quantum Howe duality, we can try to characterize the invariance in the in our calculus. So this exterior algebras corresponding to holomorphic and anti-holomorphic forms have a nice decomposition into reducible parts, which are labeled by partitions that fix in this box. So it's M by N minus M box, and lambda T is transposed. Note that automatically from this decomposition, we have the fact that this decomposition is multiplicity free. And the whole calculus, its local part, could be considered as a braided tensor product, well, with some tricks, of these two quantum exterior algebra of holonomic and anti-holonomic forms. So that means that we can characterize all invariants like in this calculus by the following ways. So first, they labeled by partitions that fix in the box that appears in the quantum Howe duality. And the recipe is the following. So take some irreducible submodule in exterior algebra of holomorphic forms. Choose a basis. Choose a corresponding dual basis in a dual module, because we know that these two guys are dual as modules over quantum Levy. And consider the following element. Well, it's easy to check that it's invariant, and it doesn't depend on the choice of the basis, because when you choose a basis, the corresponding scaling takes care about it. So, about algebra of invariance, we know at least its basis. Now we want to consider multiplication rules. There is funny calculations that say that you can reduce everything to computations in the corresponding quantum exterior algebra of holomorphic or anti-holomorphic forms. Here we use the result that every invariant should be necessary at central, because these all guys are closed forms. And with a bit of tricks, because our quantum Levy subalgebra is much better, is a special case, we can reduce computations from the quantum exterior algebra of anti-holomorphic forms to just a part of it. And the part that a huge part of the proof is using the theory of crystal bases, but I will need probably 2 lectures to explain everything. So to describe multiplication between these guys, we basically should choose now not any basis, but the corresponding global basis in these modules. And this global basis will behave nicely with respect to tensoring, and our quantum exterior algebras is a quotient of it, so we can take a projection. So it allows us to show the following theory. So first ingredient, let's consider the grothendieck ring of type 1 finite dimensional representation of GLM. So it's generated by a tautological representation and trivial. It's a monoidal category. So we have this monoidal category. We have the following ring structure. So sums correspond to direct sums of representations. Ring structure multiplication correspond to tensoring. Simple modules form a basis in this ring. And multiplication of simple modules genored by Littlewood Richardson coefficients. And main theorem of my talk is that there is a map which tells us that described in the following manner. So we take some irreducible, some element from this ring labeled by irreducible module, and we map it to the algebra of invariance if and only if this partitions fits in this box, otherwise it's 0. And this is ring homomorphism. So basically, our algebra of invariance is a quotient of this ring. And it's exactly what happens classically. So modular conjecture that all our cohomologies of quantum Grassmannians should have invariant representative, we proved that the cohomology ring of the quantum Grassmannians is amorphic to cohomology ring of the classical Grassmannians, which was a bit surprising from a point of view that we throw a bunch of Q's now and there and everything was non-commutative, but there is a nice metaphor for this. So we speak that our Schubert calculus is such a nice object as a diamond. And if you will put it in a bag, you can deform a bag, but diamond will keep its shape. On this poetic note, I will stop. Thank you.
I disagree on the statement of the surprise because actually, see, this statement by the relations that are with quantum Bucher are essentially the same. The straightening is more or less the same. So why do you want to should be different, right? I mean, it's based on that.
Well,
the king and classes, right? I call this the word surprise, not the sound.
You could be even more unpleasant saying that, well, let's look at the Gerstenhaber cohomologies. So this ring does it.
Because I work on the Bucher that quantum, but then it's the same, right? I mean, it's the same.
Well, it could be, well, first of all, many things could happen. For example, it could have a different dimension or something could collapse. So, for example, in the simplest case of Grassmannians 4-2, you can do almost everything by hand without using any global basis. But then you almost stuck to the one point when you're getting some ring with, you need to just say your scalar is 0 or non-zero. And if it was 0, then it would be some easier commutative algebra. So yeah, conceptually, it's not so surprising, but still it is. Thank you for the question.